Where's my cursor? Come on, guy. All right, there it is. Okay, so Emma and Alexi left off last Thursday talking about sort of coming to this conclusion. I can't remember if this was their exact last slide, but essentially you guys had worked through this process of looking at F equals ma, force equals mass times acceleration, along streamlines. And that came to what these two different versions of the Bernoulli equation, and they're only different in their units. Okay, so this top version is in units of pressure or dimensions of pressure. And so you can see, obviously, we have pressure by itself. We have 1/2 rho v squared, and then we have gamma times z. All right, and so if you work through all the units on these, you would basically get pressure units. So a force per area. Alternatively, we can divide through by the specific weight, and when we do that, we end up with P over gamma, V squared over 2G, and so remember gamma is equal to rho times G, so we just end up with G in the denominator, and then Z is by itself. And we call these heads, okay? So these are the same three representations of energy, and we'll talk about what these are in a moment. I mean, obviously there's pressure, there's velocity, so a kinetic energy, and then Z is representing a potential energy. When we divide through by gamma, of course, we're doing that for the fluid that's moving around. So it turns out from a units perspective or a dimensions perspective that when you divide through by gamma, you end up with just length. So each one of these, this comes out to dimensions of length, and this comes out to dimensions of length, and this also comes out to dimensions of length. So we obviously, if we're adding these, they're just consistent, right? We end up with some constant value, 3.82 meters, something like that, right? And it has to be the same along the streamline. Eventually, I'm not even going to write this down yet, but eventually we will talk about how we incorporate losses of energy, things like friction or losses due to other, things in the flow. Right now, we're going to forget about those and just focus on these three types of energy at the moment, all right, and how they offset each other. So that's why this constant along a streamline is sort of key here at the moment. All right. So these are both slightly different forms of the Bernoulli equation. All right. Real quick, I just want to we're gonna go through some problems today that require one other thing that we haven't talked a lot about, which is the continuity equation. And the continuity equation, as you would expect, essentially says that within a control volume, let's say, that is represented by this shape here on the left-hand side, what looks like kind of a lampshade. If we have fluid moving in from the bottom and moving out the top, there's no place to store that fluid, right? It comes into that volume, but whatever gets moved in from the bottom, that's equivalent amount of mass has to be moved out the top as well. And I want to focus on the mass part of this. So if we can agree that the mass that comes in has to equal the mass that goes out, then we can represent that with some of the terms that we've talked about already. So the mass in can be represented as a cross-sectional area, A1, times a mass inflow rate. And we can represent that by rho times the velocity at 1, okay? So rho V1 is basically a mass flow rate. So we would basically, let's see, if we work that through, we'd get, I think, mass per time is what the dimensions would come out to be. Oh, and the other thing I should note is that this is an A1, right? The cross-sectional area compared to the movement of water here is changing from A1 to A2. So A1 is larger than A2. And this would be equal to A2 times rho V2, right? That should be a 2. Okay, so we know that the density hasn't changed. The water that comes in is perhaps going to be the same water that's going out, right? And therefore, density shouldn't change. Therefore, for any change in area, we have to have a proportional change in velocity to make this continuity requirement true. Okay, so on the left-hand side, obviously we can get rid of the rows on each side, and we say that A1 V1 is equal to A2 V2. So this is the cross-sectional area multiplied by the mean velocity at each of these two cross-sections. Now, the other way that we can define this is that the cross-sectional area multiplied by the velocity ends up being Q. Q1 is equal to Q2. So Q is a flow rate, and it is in length cubed per time dimensions. Right? Does that make sense? So it would be like cubic feet per second, cubic meters per second. It could also be liters per second if you had really small flows, okay? Where a liter is not length cubed, but it is a volume amount, all right? So for incompressible flow, because rho 1 equals rho 2, I guess I already did this above, but essentially this is just to complete this. I sort of did it up there. A1 V1 is equal to A2 V2. So we're going to use continuity a little bit to solve some problems, all right? And the first one actually comes from your book. This is just a demonstration of kind of working through how acceleration works along a streamline, okay? And it's going to seem a little torturous, but stick with me, because at the end of this, I want to make an important point, which is the proof that that these energy amounts essentially change from one location to the next. All right. So here's just an example. Water flows steadily through a variable area pipe, so not unlike what we just saw. And if we go from point 1 to point 2, now we're going from, actually similar to the previous one, a larger area, cross-sectional area, to a smaller cross-sectional area 2, because we're moving from left to right here. The centerline velocity is given by this equation. The velocity vector is equal to 10 times 1 plus x, and then we have the I hat sort of x direction unit vector there, and it's in feet per second, right? So from some reference point 0, as we move further down in the x direction, we would see the velocity change, all right? And you can see that if we put in 2 for x, we would get, 30 feet per second. And if we put in 3, we would get 40 feet per second. So you can see that velocity is increasing as we move, which makes sense because we said that the cross-sectional area is narrowing, it's getting smaller. Therefore, velocity has to increase, okay? And so what we're really looking for is what is the pressure gradient as a dp dx, so in other words, in the x direction, needed to produce this flow. So figure this out in pounds per cubic feet. Now, what we really mean here is the pressure, remember, is in, well, let's just do this in units, not dimensions, pounds per foot squared. And what we're looking at is dividing that, or looking at how that changes per foot, right? So that's how we get pounds per cubic foot. This isn't necessarily a cubic foot like in this cubic foot of water, how is pressure changing? It's more, how is pressure changing in pounds per square feet per foot that I move in the direction downstream, all right? So let's just go through this math real quick. And this goes back to the part of the derivation that Alexi and Emma did last week, which is why I wanted to return to this and work it out. So V, we said, is equal to 10 times 1 plus x, and we said it was, we multiply it by the I unit vector because it's going in the x direction, all right? Now, one of the equations that they ended on, I think before the slide that I started with, looked like this. It said we had a minus gamma times the sine of theta minus del P del S, so the change in pressure along a streamline is equal to rho times V dV ds, or del V del S. Okay. Now, in this case, we have a horizontal flow path or streamline. Okay. So because we have a horizontal streamline, theta is essentially equal to 0, right? So if we took the sine of theta, what would we get? We would end up with 0 essentially, right? So that first term ends up going away in this case because we don't have any curvature to our flow path here. And so we can now rewrite this to basically say that del P del S, del S is equal to minus rho, our density, times v, the velocity, times, I'm going to go back to the del notation. I think it's just a little more pure. Del v, del s, so the change in velocity along our flow path length here. And we're going to now try to simplify this. That's supposed to be an arrow, to say that del p del x, and I've replaced x or s with x, okay, because we're moving in the x direction, is equal to minus rho times v, the velocity, and that's this expression up here, del v del x. So what we're going to have to do is take the derivative with respect of this equation up here for v with respect to x. Okay, so this is equal to rho times 10 times 1 plus x, and then we multiply that by the derivative of this with respect to x, just comes out to be, let's see, is that multiplied? Yeah, let's multiply by, just multiply by 10, okay? So we took the derivative here. That was actually pretty simple for this expression for v. We plugged in v, and we still have rho. So all of that is just expanding that or substituting in for the general equation there. All right, so we can now say that the pressure gradient in the x direction is equal to, I'm going to plug in rho. So remember, in English units, the density of water here is equal to 1.94 slugs per foot cubed, right? So I'm going to plug in for rho here. We're going to have minus 1.94 slugs per foot cubed. And then we multiply by, basically, I'm just going to multiply that 10 together. So 10 feet per second, and we're just going to put a square out there because the two tens will multiply. And then we're going to multiply by x1 plus x. Whoops. 1 plus x. Okay, so this is what this expression looks like. We can obviously simplify this a little bit more. So it's equal to minus 194 times 1 plus x. And if we multiply these feet squared per second squared times slugs per cubic foot, what we end up with is units of pounds per foot squared. And I think I got that wrong. I think this should end up actually being per cubic feet. Okay, I think my notes are wrong. So we end up with, so there's the answer. There is the pressure change as we move along the x-axis. The reason that I took you through this is partly to link the derivation to this meaning. And the meaning is that as you move forward in x, we said that velocity has to increase. And at the same time, the pressure has to decrease. If these are the two types of energy we have, we don't have a change in elevation, right? So there's no change in potential energy. Then the pressure energy and the kinetic energy have to change to offset each other, all right? And that offset then is to say that if velocity increases as I move in x, this is the decrease in pressure as I move in that direction. Okay, so as V velocity increases, P the pressure decreases along the streamline. All right.
Professor?
Yeah.
Okay, so just to get back to the derivation on Thursday, so this equation is from Thursday, you're saying?
I think so. I thought I saw this at the end of what you guys were working on. Am I wrong?
Yeah, there's like it's like the F equals MA equation that's just been like expanded out, right?
Yeah, so there was a point where I think you guys said, like, I thought I remembered in the video you even talked about like the getting that rho v dv ds, that came from calculus, right? Because you're basically representing dv ds as the acceleration.
Yeah. Okay, so this is on page 25 of the notes. Okay. Some people were confused, and then I wanted to make sure.
Okay. Yeah.
But just to let everyone know, that's where it is.
Yeah. Sorry. I did actually add this problem into the notes today, and I apologize for that. I just wanted to make sure that we went through it because I thought it was an important illustration, and you have one of these on your homework, and I just wanted to make these not seem particularly scary because when you start with a velocity representation like that, it can be a little bit onerous. And so I just wanted to make sure we went through this to kind of demystify that a little bit. So yeah, thanks. Sorry, this might be a slightly different than what we had in the notes. Okay.
Someone asked, did you change ds to dx because ds is position?
Sort of. The reason, so I sort of mentioned this in passing, but I changed S to X, and that may have been not very clear because they sound so much alike, because we were only moving in the X direction. So S is along the streamline, S like Sierra is along the streamline, X like X-ray, we just happen, those are coinciding, so I just kept it as X. Yeah, good question. Okay, terrific. Okay, this is going to look up, oh, sorry, I gave myself a second slide. We ended up not needing it. Okay, this is, I want to write this in a slightly, you have a page, I think in your notes that has this equation or this kind of layout, and what we're going to do here is talk a little bit about how the force equals mass times acceleration across streamlines, not just in line with the streamline, but also across, all right? And we're going to start this with a force balance that basically says that my forces, the sum of my forces in the normal direction here. So now normal, oh my goodness. Normal, remember, is going in sort of this direction. Like, oh, this is our fluid particle, remember. It's on some streamline that's indicated by this blue path right here. That's our streamline. And remember, normal to the streamline is essentially what we're looking at here. So the sum of the forces in this normal direction are equal to this delta m, so some infinitesimal mass times an acceleration in that normal direction. Okay, so, oh, good heavens. Some of the forces in the n direction then are equal to, we can take this, so that's the F or m times a on the right hand side. We can also say that this is equal to delta w, so the weight component in the normal direction, plus an infinitesimal particle force, or pressure force, pardon me, in the n direction as well. Okay? And so what this boils down to, and by the way, this FPN is essentially this force here and this force here. Okay, so those are those two pressure forces acting in the opposite of each other in the normal direction to the streamline here. And so we can basically simplify this a little bit to say that we have minus gamma times the cosine of theta here, minus del P, the pressure gradient in the n direction, del N, times some delta V volume here, okay? So this theta, remember, is based on this orientation indicated in the middle here. So weight is acting directly down. We need the component that is acting in the n direction. So that's all that the first part is basically accounting for the weight component that's only acting in the n direction. We multiply gamma by volume, the specific weight by volume to get that weight amount, right? So we've simplified by removing gamma from here. We've also removed gamma from this term, where now we're just looking at the pressure difference between these two forces that are acting on the top and bottom of this infinitesimally small fluid particle. All right. So now, simplifying and combining the previous equations, what we end up with is minus gamma times del z del n minus del p, the pressure gradient along n, is equal to rho times v squared over r, the big radius here, for this curvature that comes from the current streamline. All right, and if we integrate this, we essentially end up with something that will look a little more familiar: p plus rho times the integral of v squared, velocity squared now, v squared over r dn, so with respect to the normal direction, plus gamma times z is equal to a constant across streamlines. Okay, so what Alexi and Emma did last Thursday was talk about along streamlines. This is across streamlines, so now working normal to that direction. So what this means then is that a change in direction of flow of a fluid particle, for r being something less than infinity, which was horizontal, remember, is accomplished by a combination of pressure gradient and particle weight normal to the streamline. Okay, those two kind of forces acting against each other. All right, and I apologize, that looks terrible. This is supposed to just be the integral sign for v squared over r, velocity there. Okay, so we have this representation. This comes back to a representation of the Bernoulli equation that you all looked at before, which was essentially this one: this minus gamma times sine of theta minus dp ds is equal to rho times v dv ds. And we're going to substitute two things, but essentially what we end up with from these two, and again, this is just going backwards a little bit, just so we recall where we were: minus gamma del z del s minus del p del s is equal to 1/2 times rho times del s of v squared. Okay, which is the longer way of writing this equation out, the Bernoulli equation. This is the non-simplified way, but essentially this is where it all comes from. All right. So, what does all this mean? Let's now start to talk about a couple of fundamental assumptions that are here that we're going to apply for now, so that we can simplify the way in which we apply the Bernoulli equation in some specific cases. Okay. All right. So the first thing we're going to assume is that we have steady flow. And what steady means is not space, but time. So in other words, there's what we would say is dq, the change in discharge with time, is equal to 0. Okay, so there may still be differences in velocities at different places within our flow, but the rate of flow does not change with time. All right. So we have steady flow, number 1. 2, we have inviscid flow. And the inviscid flow part here is just indicating that we're not going to worry about viscosity, right? The viscosity would add a bit of a drag here. So we're going to ignore the viscous effects for the moment. Third, we're going to expect that we have, we're going to assume that we have incompressible flow. And when we have incompressible flow, that means that our density doesn't change from one point to another, and therefore our gamma doesn't change, right? Our specific weight, okay? And then finally, we are going to assume that 2 points, and we're going to call those point 1 and point number 2, are along the same streamline. Okay, so now what I'm going to do, we've written the Bernoulli equation kind of by itself. Now we're going to write it between 2 points, all right? And this is sort of an important segue here. So we can say, I'm going to write this 2 ways, the pressure way first and then the head way. So the pressure way is P1 plus 1/2 times rho V1 squared plus Z1 is equal to the same parameters, but at point number 2. So P2 plus 1/2 rho V2 squared plus Z2. Okay, so, sorry, I did forget my gammas. Thank you. I don't know if somebody mentioned that, but that should be a gamma. And I'm going to put the gamma afterwards here, just to make it look a little better. All right. So in the pressure version here, adding these up means that basically between 2 different locations, as we saw a moment ago with that little example we did, the pressure can go down from point 1 to point 2. The 2 pressures can be different. But if that's the case, then there has to be a change in either the velocity component or the potential energy component, so that the sums of all 3 of these energy types are the same at both locations. Okay, so the other way that I'd kind of like to work with this in head units instead is P1 over gamma plus V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. Okay, so Z1 and Z2 are just elevations. V1 and V2 are the velocities, the mean velocities at those 2 locations, wherever point 1 and point 2 are. And P1 and P2 are the pressures at those locations. But what we're going to do in the next several slides is sort of think about what each one of these mean and how they relate to each other and to things that we've seen before. In particular, thinking a little bit about manometry, for example. All right. Okay, I think this is a slight bonus one for your from your notes, but all I really want, the bottom part is the most important. I'm going to rewrite the equation again, but you've seen it several times. So P1 over gamma plus V1, oh, goodness, okay. V1 squared over 2G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2, okay? So the pressure head component of this is P over gamma which is also something when we put in a manometer, we have called H before, okay? So just some H value, some height in a tube, and we'll talk about where we apply that. Velocity head represents the vertical distance needed for the fluid to fall freely, neglecting friction to reach velocity v from rest. So this is the v squared over 2g component. All right, so these are just ways of verbally interpreting what these different heads mean. And then finally, the elevation head represents the potential energy of a fluid particle in terms of its height from a reference datum, and we just represent that with z. But one of the things that we often do is say, you know, my Z1 is lower than Z2. I'm going to call that my zero, right? I'm going to look at how Z2 is different than Z1, but that means I can cancel out Z1, make it zero, and sort of make things easy. In that example we did a few slides ago, everything was horizontal, so we didn't have to worry about Z, which was kind of nice. All right. I'm going to write these words, and you can decide how much you want to write them as well. We've said this a couple of times, but essentially what the Bernoulli equation means is that the sum of the pressure head, you know, these three heads. So the pressure head, the velocity head, or kinetic head, should be a C, and elevation head, is constant along a streamline. And what this also means is essentially that, let's do that, i.e., energy is constant along a streamline assuming no friction or any other kind of loss. Okay. Another way of saying this, energy is conserved. That's essentially all this says, is that I might change my type of energy between two places, but the energy is conserved. All right. It just changes form in some way.
Professor,
yeah.
Can you go back a slide for a second and move the iClicker thing? Because I think it was blocking the text.
Oh, sorry. Yeah, it's funny. It doesn't. Yeah, okay. It does. Of course, it doesn't come through on there. There. Thanks.
And I think people just wanted to write some more stuff down.
Yep. No problem. Okay, so we have a pressure head, a velocity head, and an elevation head. And again, a change in one has to cause some kind of change in the other. The elevation head is, going to largely be driven by the system, right? Like the pipe goes up or it doesn't, or it stays horizontal or it goes down. There's less opportunity for the fluid to decide sort of what to do there. But when velocity increases, pressure can decrease more easily. Okay. Let's take a look at this video because it's pretty instructional, in my opinion, for, oh dear, I can't get it to run. Oh, I know, I guess I have to go out of, sorry, I've got to go out of pen mode. Pen, nope, come on. Okay. Yeah, that's weird. Oh, here we go, arrow. There we go. All right, so these are streamlines of flow that has been labeled around this wing. We're kind of looking at a cross-section of a wing here. And what you can see is that along these streamlines, they bend around this particular object, as you would totally expect, right? We are ignoring the possibility of the engine underneath falling on your yard and broom field if you what happened this past weekend is any indication. But there are two things I want you to notice, and I'll try to stop this at the right location here at the end and point them out. But each one of these streamlines, they're a little bit thick, right? But it makes it easier to see them. As we get to the end here, I'm going to have to choose it over here. A little bit further. I want to try to stop this before we get to the credits. There, let's just choose that. Okay. A couple of things. Note that let's go back to the pen. Okay. Note this streamline here hits the front of this and goes around the wing. This one right below comes up, hits underneath, and sort of hugs it, and then moves down. Okay. We can call there is one little point somewhere in here that's a stagnation point. It's a point at which flow hits it and just separates around. Okay, so there's a point there, and we start to see them reconnect sort of back on the tail end, right? Somewhere down in there is where these flow lines will sort of come back together. Now, for the most part, these are all moving parallel to each other, but clearly, because of this object being in the way of the direction that all of these were originally flowing from the left to the right, there's been some deformation, right? We had some changes in the Y direction, or Z, depending on what we want to call it, compared to the X direction that they were all going when they started. And so what's important here then is that these pressures, the pressure field is changing as we move and get closer to this, to the front of this wing. And then all of those changes are sort of evolving as we move along the wing until eventually we can get back to more or less horizontal flow lines that are more or less equally separated on the right-hand side of this, right? But there is some changes that have been made just because the wing is there. Without the wing, these would all just kind of look like I guess music with no notes, right? Just lines going parallel to each other. Okay. All right. Well, let's talk a little bit about how we measure static, dynamic, and stagnant pressures. And all of these are important ways of applying Bernoulli's principle and equation in the real world to come up with velocities or pressure changes or what have you. And so on this diagram here, we have a couple of things that are shown. We have two primary I guess we could call them apparatus. The first one is a pressure tube on the left, and you can see that the tube is kind of like our manometers, right? Like we just have some an opening there, and there's some rise of water. Let's say it's water flowing in this pipe from left to right. It rises up to some level there. That should all be still. Right? There's not water moving to fore and then evaporating. It's just risen up there and then it's kind of hanging out. All right. The water that's moving is moving from left to right in the pipe down below. Okay. So just to reinforce these arrows here, essentially we have a velocity v that's on the right hand side because we're not changing the cross section of this shape at all. This pipe. But then we have this stagnation tube on the right-hand side. The stagnation tube comes down into the flow. In this case, it's shown to be right in the middle. And you can see that because we are standing up some water here, right, to some height h, we also have a zero velocity right out in front. In other words, we're going from a transition where everything else is going by, but the water that comes here, this is where we have that separation occurring, okay, just like the wing. The flow line that comes into, that reaches the front of that stagnation tube has to split and go around. So there's a stagnation point right there. All right, so what we're going to do is talk about we're going to prove to ourselves how these two things work and what they show differently. And I'm going to, on the next two slides, I've taken this picture and I've cut it in half. So we're going to talk about the static pressure tube on the left-hand side first, and then on the right-hand side, the 2 slides from now, we'll look at the stagnation pressure tube, and we'll use Bernoulli's to tell us what is being shown here. Okay, so the static tube measures what we call, perhaps not surprisingly, static pressure. And static pressure is really just P, pressure here. Okay, note, as we talked about before, for straight streamlines, or horizontal, I guess would be the better way to put it. No, actually straight works. Straight streamlines the radius of curvature is equal to infinity. Okay? So now what we're going to do is talk about, basically, we're going to apply this F equals M times A across streamlines. Which is sort of what we started with today. And this will reduce to P plus gamma times Z is equal to a constant. Okay? So, in other words, let's apply the Bernoulli equation now, or this representation of it. So there's no interaction with velocity here. Okay, we are sort of taking the Bernoulli equation and we're simplifying it. All right, so we're going to apply this. Oops, got an L in there. Apply from location 1 to location 4. Okay, so what we write here then is that we have P1 plus gamma times Z1 is equal to P4 plus gamma times Z4. Okay, now one of the ways that we can help ourselves is to say that this elevation at Z1 is our datum, right? That's Z equals 0. So Z1 is, if Z1 is equal to 0 relative to Z4, then we can cross out the left-hand side. And remember from our manometry, the pressure at 4 is going to be equal to atmospheric. And so in a gauge context, we call that 0, right? So this can simplify to 0 as well. So what we end up with then is P1 is equal to gamma times Z4. Yeah, gamma times Z4. And we know that Z4 essentially equals H. So another way to write this is to say, if we combine these two, we say H is equal to P1 over gamma, okay, the specific weight of our fluid. Now, the reason this is important is because we can just use a simple manometer coming into the edge of the side of the pipe to basically tell us what the pressure is at that cross section. All right, nothing about velocity. We don't get velocity until we get to the stagnation tube, but the static tube helps us with this component. Okay. And this, by the way, this H is something, is the rise in height due to static pressure head. Okay, so kind of the cool thing here is when we were looking at P over gamma in the Bernoulli equation, you might say, well, that seems kind of esoteric, but the true measurement of it is something that can be made with just a manometer sticking out of the side of the tube. The part of the entire rise of the water in that tube is due to, or the fluid in that tube is due to this static pressure head. Okay, so that's where that gets represented. Okay, next let's talk about the stagnation tube. So what I've done is I've taken now we're not going to see this part of the full, what do you call it, figure, and I've just cut off this and we're just looking at the right-hand side now, the stagnation part here. Okay, so now we have the stagnation tube, and you may recall from manometry that P2 in this case is equal to gamma times capital H. So in other words, in this stagnation tube at point number 2, we have a velocity of 0 right in front of it, and the height of this or the pressure, we can relate the height to the pressure as P2 is equal to gamma times H, all right? So, so now, in this case, instead of going across streamlines, we will apply Bernoulli. For shorthand, I'm just going to say the Bernoulli equation B dot E dot along streamlines. And I guess I cut it off. We're actually going to do this from location number 1 to location number 2. So sorry about that. I guess I can put the parentheses around these. Okay, so somewhere upstream at 1 where things were flowing freely, we can write P1 over gamma plus V1 squared over 2G plus Z1, and ultimately Z1 and Z2 are going to be the same, but I'll write them out for the sake of argument here, or the sake of completeness, is equal to, and then we said P2 is equal to gamma times H. So rather than writing P2, I write gamma H over gamma, right, plus V2 squared over 2 times G plus Z2, okay? Now, Z1 and Z2 are going to be the same because they're on the same elevation. So whatever one is, the other one is the same, and on both sides of the equation, we can cancel them. We said that V2 is equal to 0, so that part of the equation goes away. And now we're left with essentially this, well, I guess to be careful, let's cancel those out as well. So now what I'm going to do is rearrange this and put H on the left-hand side and say H is equal to P1 over gamma minus, plus V1 squared, V1 squared over 2 times G. Gosh. Okay. So this means that H represents the static. This pen is not keeping up with me, or rather, the screen is not. Static and velocity heads. I have to go so slow. And it's still missing me. So those two heads together. So the stagnation pressure is essentially equal to the static pressure plus the dynamic pressure. So stagnation pressure is equal to, really? Gosh. Boy, this is annoying. Okay. Come on, that's supposed to be a C of all things. Static pressure plus the dynamic pressure. Ugh. I feel like I'm trying to make something kind of frustrating to write. Okay, so hopefully that was slow enough for you guys to keep up. So in other words, this capital H, which of course was bigger than just the static component, is now including this velocity head because we have that pressure that is pushing up against the opening to our stagnation tube. Okay, and the stagnation tube obviously isn't just coming out from the side of the pipe anymore. Now it has to come down and interface with the flow. All right. One thing that you may be familiar with on the front of like helicopters or other aircraft is pitot tubes. Pitot tubes is essentially one of these. It's a little tube that sticks out, and you're trying to assess the pressure up against the front of that to figure out your velocity. Okay. I think this is another added one that I didn't put in your notes, but it's super simple, and I just wanted to apply Bernoulli's equation in a really simple way to demonstrate how straightforward it is. So we could probably do all this in one, just on this slide, but if you just draw that little picture, the question is, recall that we said Q is equal to the velocity times the cross-sectional area, the mean velocity times cross-sectional area. Can we apply Bernoulli's equation if we know the diameter of this? So we know the area. We can calculate the area, pi over 4 times, in this case, 0.75 inches squared. Can we use the Bernoulli equation to figure out what the velocity is that's coming out right at that point, so that we know that 2.8 inches is somehow indicative of figuring out the velocity here, the total energy change. So what we're going to do is call this point number 1 and this point number 2, okay? And we know a couple of things. The first is that the pressure at 2 is equal to 0 because it's open to the atmosphere. But it also turns out that the pressure at 1, as you leave the pipe and go into the air, is also equal to 0. Okay. So automatically you can start to think, oh, we're starting to get rid of things in that six term equation that will simplify it. And that's exactly what we mean to do here. So P1 over gamma plus V1 squared over 2 times G plus Z1 is equal to P2 over gamma plus V2 squared over 2G plus Z2. Okay. Now, if we also call this our datum, so Z equals 0 here, then Z1 is going to end up being 0. We've already said that pressure 1 goes to 0, pressure 2 goes to 0. The other thing to note is that at the top of this sort of jet of water, that velocity is now equal to 0 as well. Okay, so V2 is also equal to 0. All right, so now we've made this super simple. V1 squared, or V1 squared, I'm going to move the 2G over, is equal to 2G times Z2. Oh, goodness sakes. Z2, or V1 is equal to 2G, oh, that shouldn't be squared. Sorry, that should have been down here. 2G Z2, and we just take the square root of that product, right? And so the height of that water is indeed directly related to the velocity of the water coming out at the tube, in this case, by a square root. So if we do this math real quick, basically we find that V1 is equal to 2, we're working in inches and pounds here, so we have 32.2 feet per second squared is the acceleration due to gravity in English units. We multiply by, I'm just going to make my conversion in here, 2.8 divided by 12 is Z2 in feet, right? And then we take the square root of that, and we end up with 3.88 feet per second. That should be an S, feet per second. And then Q, the flow rate, is equal to A1 times V1, which is equal to pi over 4. And we multiply by, again, I'm going to do my transition here, my conversion, 0.75 inches, leave the inches out. If we just divide by 12, we can then just put feet here, right? That's the actual value in feet. And we square that, and then we multiply by 3.88 feet per second for our velocity. Wow. That's supposed to be an F, and that's a T. Goodness sakes. I feel like, okay. And we just put that on the end. So this comes out to be actually a pretty small flow of 0.0119 cubic feet per second. That's supposed to be a 3. And that's supposed to be a Q. And that's supposed to be an S. Goodness. Wow, where did my other 0 go? Okay, 0.0119. Okay, so the next thing that we should move on to is talking about some other examples like a free jet, which is back in your notes. I'm gonna move ahead. I'm gonna jump ahead to our clicker question because we just have 3 minutes left, and I wanted to make sure that we get through this. So, all right, in low speed flow, the following device is called a diffuser. So, in other words, it expands out. And the question is, the fluid velocity then A increases in the direction of flow, B decreases, or C stays the same, or D, none of the above. So go ahead and get your entries in on that. And I've got one more right after this too. All right, 35 seconds, 36. We'll go for another 23 seconds here. Think it through. A is increasing as you move downstream in the direction of flow. Okay, we've got 86 responses. I don't know how many people we have online right now, but we'll go ahead and end there. All right, and we end up with B being the most popular. And indeed, the fluid velocity would decrease in the direction of flow because the cross-sectional area is increasing, right? So for the same amount of fluid or mass you put in from the left has to go out on the right, therefore we have to decrease velocity. Okay, great. Let's do one more. I just have it on the next slide here. Now, what happens to pressure? All right, so the question is, in a low speed flow through a diffuser, the pressure A increases with the direction of flow, B decreases in the direction of flow, C stays the same in the direction of flow, or D, none of the above. Okay, so we just said that velocity decreases, so what happens to pressure? And we can think about these in terms of velocity head, pressure head, but pretty much everything else that we put into those terms are constants, right? So just dealing with the pressure and velocity should be enough to make this determination. Okay, we're up to 81. Perhaps we lost a few. 83. If we get up to 85, I'll call it good. Oh, we are. There we are. Okay. So we've got actually a pretty good split here now. So A, it increases in the direction of flow. B, it decreases in the direction of flow. C, it stays the same in the direction of flow. Okay, because we have P1 over gamma plus V1 squared. Oh, goodness. V1 squared over 2G. The Z's will cancel out. So P2 over gamma plus V2 squared over 2G. If V is going to decrease from 1 to 2, then P has to increase. So this is just a way of thinking about how these three energy types are compensating for each other. When one goes down, something else has to come up for it to be constant along this flow line or along this streamline. And so in this case, for V to go down, P has to go up in this case. So this is the first time we've actually had a majority choose the wrong answer, but that's okay. This is low stakes. You're just trying to learn from it, so no worries at all. We don't know who you are. We just know that you voted, so that's what matters. All right, let me just wrap up with the final slide. I don't know why I was on the wrong keyboard. Let me just wrap up with. Oh, really? Oh, now I can't get back to it. I'm just trying to get to my final slide. I just wanted to note what was coming up soon. Really? Okay, for some reason I can't go back to that. So, all right, let me move this over. Okay, so the wrap up for today is just homework 6 is posted. We'll obviously, Alexi will hold office hours on Monday as usual. We'll have recitation Monday afternoon, so we'll see you at 4 o'clock there, or 4:10. And other than that, I'll be happy to stick around for questions. So have a great weekend and stay safe out there. Stay warm. Take care.
Thank you.
You bet.
Thank you.
Stop sharing here.
Thank you.
Great. Take care.